Now that we've introduced the basic idea of the electric potential, let's start looking at the electric potential of different scenarios. We're going to start with our parallel plate capacitor. And remember that that gave us a uniform electric field. And we know that that electric field was equal to eta, the surface charge density on these plates. And by definition, our eta must be equal in magnitude, opposite, and sign on the two plates. And so that's eta over 2 epsilon naught. And this is coming from summing the field from two infinite planes of charge. Each of those would be eta over 2 epsilon naught, and so when you sum them, you lose that 2. Remember that the direction is from positive to negative, and it's exactly perpendicular to the planes. This has been calculated for an ideal situation where we have infinitely wide planes, and that's valid as long as they're fairly closely spaced together or we're near the center. So what we need to start talking about is, again, that idea of source, that our field source is the capacitor plates. If I place a little point charge between them, then this is going to experience a force due to the field. We would call this the test charge or the probe charge. So similarly, as we talk about electric potential, remember that if you do have a point charge here, the potential we're talking about is due to the source, which are the planes of the capacitor. So what is the electric potential from a capacitor? We talked previously about the potential energy from a capacitor, which was equal to Q, where this is again of our point charge, of our test charge, times the electric field, times the distance, where that distance is from the negative plane. So that was covered in a previous video. The definition of electric point charge is that you take your potential energy and you divide out Q. So we're left then with a fairly simple thing, that the electric potential of our capacitor, which I'm attempting to write, is equal to the electric field, or the magnitude of the electric field. In this case, we're not going to say positive or negative, times the distance from that negative plate. So this is a linear potential. We have a constant, a uniform electric field. We're multiplying it by a distance, so that means our potential, we could say, starts at 0 here and then increases. Now, there is going to be one caveat that we can always define this to have some sort of offset, which we'll talk about later. But we do have then this linear relationship that goes from the negative plane to the positive plane. So if we go back and think about field, we know that our field is uniform, and we can actually calculate the field to be the difference in potential between these two plates. And note that it's plotted this way, right? We're effectively plotting potential on the vertical axis and position on the horizontal. That the difference in potential between this right plate, which is here, and the left plate, which is here, is just given by delta V. And we do subscript C to imply that this is of the capacitor. So this is an interesting value because when you build a circuit, you don't necessarily know what the electric field is within that capacitor, and you will later be encountering capacitors within electronic circuits, but we actually can control, or we know, this potential difference. And the spacing, d, is a physical parameter of the capacitor. So frequently we're actually going to define the strength of the electric field in terms of the potential difference and the distance. Now notice that once you do this, we can actually define a new unit of electric field. This is actually going to be the electric field unit that we're going to use more frequently. So our previous unit of electric field was coming from the idea that it was related to force and charge. Now we have a unit of volt on top, and again remember that V is getting used both for potential and for volt. And on the bottom you would have meters. So another unit for electric field is volt per meter. You're actually going to see that more frequently, and that really is the same if you break it into its fundamental SI pieces as a Newton per Coulomb. So two different units mean the exact same thing. This is a little more common.